Hi, this is Charlie, and today we're going to go over the instructions for Lab 3, Insolations and Seasons. So we're going to look at the analemma, which is a diagram that shows the location of the subsolar point throughout the year. We're going to look at how to calculate noon sun angles, which is the angle of the sun above the horizon at noon. And we're going to look at patterns and how to read a diagram showing daily insolation values. So let's start with the analemma. Again, diagram that shows the location of the subsolar point. So there is the diagram. I grab the pointer and I'm going to go through this, but around the outside there's dates. August, September, October, November, December, January, February, March, April, May, June, July. So there's dates and months around the figure 8 of the diagram. Across the top, there's the equation of time. We're going to completely ignore how fast or slow your sundial would be. And along the left-hand side, there is the declination of the sun, which is the latitude of the subsolar point going from 23.5 north at the Tropic of Cancer to the equator to 23.5 south at the Tropic of Capricorn. So the analemma shows the position of the subsolar point. If you know the date, you know where the subsolar point is, or if you know where the subsolar point is, you know what the date is. So here's the position of the subsolar point on the June solstice, June 21st, July 21st, August 21st, September 21st, October, November, the winter or the December solstice, January, February, March 21st on the equator for the equinox, April, May, and back up to the Tropic of Cancer. So if we ignore the left-right aspects of this and just have the sun show the declination over the course of a year, you can see it goes from June, July drops a little bit, August moves a whole bunch, September moves a whole bunch. Now we're back at the equator for the September equinox, October, November. So from November to December to January, you can see it doesn't move a whole lot. From January to February moves. From February to March, we're back at the equator. March to April, we're moving. April to May, not as much. May to June, a little bit. June to July, just a little tiny bit. So over the course of the year, the rate of change of the analemma, or the rate of change of the position of the sun changes, as well as the position of the subsolar point. So, if we know the latitude, 18 north, you know what the dates are. Looks like it's May 12th and August 2nd. So you just read the dates off here. They alternate black, white, little groups of 5. So you just go, well, that would be 10, that would be 11. That's May 12th. And then August 5th, 4th, 3rd, August 2nd. There you go, August 2nd. May 11th, August 2nd. Wow, I forgot I put that there. I'm glad I was right. That would have been embarrassing. Although I would just edit it and no one would know. But I'd still be embarrassing. So if you know the dates, February 25th or October 19th, those are two dates that the sun is at the same position. Then you just slide over and go, oh, 9 south. The subsolar point on February 25th and October 19th, it's 9 degrees south. So you can also think of it from any position, for example, from April 29 into May, into June, July. If you were at 14 degrees north, from May through June, through July, through August 15th, you would have to look north to see the sun. The rest of the year, the sun would be over the southern horizon. So April, or rather August, September, October, December, January, February, March, up to April, you'd be looking for the sun. The sun, you'd have to look south. Remember, because the subsolar point goes from 23.5 north to 23.5 south. I'll talk more about this, but if you know, if your location is in between the tropics, you can use the analemma to determine what days the sun, for example, if you were at the equator, half the year the sun would be over the northern horizon, and half the year the sun would be over the southern horizon. So if you know where you are, or you know where a given declination of the sun is, you know if you'd need to look north or south in order to see the sun. That's it for the analemma. So this next part involves a lot of math. This is calculating noon sun angles. So today you're going to calculate the angle of the sun at noon for different locations and dates on Earth. Why do we care? High sun angles mean more intense sunlight. More energy is received at the surface if the sun is hitting the surface at a more vertical angle. Low sun angles mean less intense sunlight. So if the sun is lower on the horizon, in fact, so this is happening across the seasons. I mean, it happens every day, and so you know this. Like first thing in the morning, last thing in the evening, when the sun is low on the horizon, there's less energy hitting you from the sun as opposed to noon. If you went out and faced the sun when it's coming up, you'd feel some warmth, but it's nothing compared to if you went out at noon and faced the sun, the amount of energy that you would get. And that's because the sun gets spread out at low sun angles, so it's less intense. So over the year, the subsolar point moves between the Tropic of Cancer and the Tropic of Capricorn. So on the equinox, if you're at the equator, the sun would be directly overhead, hitting the surface at a 90-degree angle. If there was a pole standing at the equator, there would be no shadow because the sun, at noon, there would be no shadow because the sun would be directly overhead. But what if you're not exactly at the spot where the subsolar point is? Well, for every degree you are away from the subsolar point, so if you were 1 degree away from the subsolar point, the sun would be 1 degree off of vertical. If you were at 2 degrees latitude, the sun would be 2 degrees off of vertical, so the angle of the sun to the horizon would be an 88-degree angle. So for every degree you are away from the subsolar point, the sun is going to be that many degrees away from vertical. So we're going to find the angle of the sun at noon at different latitudes. There are 3 elements of information in this equation. If you know 2, you can solve or find the third. To find the noon sun angle, so that's 1, I put it in blue. To find the noon sun angle, you need to know where you are, your latitude, that's in green, and where the subsolar point is, that's in red. So if you know 2 of these, if you know where you are, and if you know where the sun is, you know what the angle is. If you know what the angle is and where you are, then you can figure out where the subsolar point is. If you know the angle and where the sun is, then you can find out your latitude. So let's go through this. We're about to find the angle of the sun at noon at different latitudes. You will use the following formula. The noon sun angle, which I'll abbreviate NSA, equals 90 degrees minus the zenith angle. The noon sun angle equals 90 degrees minus the zenith angle. The zenith angle is the number of degrees. When I say distance, that's in degrees, the number of degrees between the subsolar point and your latitude. So the zenith angle is just the number of degrees between 2 locations. In other words, the noon sun angle equals 90 degrees minus the difference between your latitude and the subsolar point. This has got a plus minus because it's really the difference between them, and I'll talk more about that. I'm going to use the ampersand to indicate that it's not like an add or subtract necessarily. It's just the difference between them. And the 90 minus your latitude plus or minus makes sense. If you were where the subsolar point is, the difference between your latitude and the subsolar point would be 0, and the noon sun angle would be 90, right? If you are where the subsolar point is, everything inside, where'd my pointer go? Everything inside here, if that's 0, if you are where the subsolar point is, that's 0. 90 minus 0 is 0. The noon sun angle is 0. So if the subsolar point and your latitude are in the same hemisphere, you're going to subtract. So here we have 40 degrees north, 10 degrees north. The difference between them is going to be a 30-degree angle, so you subtract the 10 from the 40. They're in the same hemisphere, so you subtract. In fact, I would probably remember it that way. Same, subtract. Because I have a small brain and it makes it easier to remember. Equinox, equator. Summer solstice, same, subtract. So if they're in the same hemisphere, you subtract the smaller from the larger because you just want the difference between them. In this case, the difference between 40 degrees and 10 degrees is 30 degrees. Ta-da! All right, well, if they're in the same hemisphere, subtract. If they're in different hemispheres, you add. So if we've got the difference between 30 north and 30 south, if you subtract, you're going to end up with 0. But really, you're looking, here's the equator. So that's a 30-degree angle. Here's the equator. That's another 30-degree angle. So we're going to add. They're in different hemispheres, so we're going to add 30 plus 30 equals 60 degrees. So the angle between them, if this was your location and that was the subsolar point, the zenith angle then would be 60 degrees. Again, the subsolar point and your latitude are in different hemispheres, then you add the numbers together. Let's look at crappy clip art together. All right, easy one. So the date, the September equinox, so we know where the subsolar point is. 40 degrees north. Yeah, I don't know what that means. I'll fix that later. So noon sun angle equals 90 minus the zenith angle. The noon sun angle equals 90 minus the zenith angle. The noon sun angle is 90 degrees minus the difference between you and the subsolar point. So in the setup, I said you're at 40 degrees north. The subsolar point is at 0 degrees. So 90 minus 40 equals 50. So the noon sun angle is then 50 degrees. All right. It's the December solstice. You're at 47 degrees north. So you're at 47 degrees north. The subsolar point is 23.5 south. So they're different hemispheres, so you're going to add. So 47 plus 23.5 is 70.5. So the noon sun angle equals 90 degrees minus the zenith angle equals 19.5 degrees. So the noon sun angle would be 19.5 degrees. All right, when I started this, I said there's 3 elements. There's the noon sun angle, there's your latitude, and then there's the latitude of the subsolar point. If you know 2 of those, you can solve for the 3rd. So what if you know the noon sun angle? And what if you know where the subsolar point is? And I don't know how you've done this, but you don't know where you are. How do you know? So there's 3 elements of information. If you know 2, you can find the 3rd. So there's the noon sun angle, where you are, and the subsolar point. If you know the noon sun angle and where you are, you can find the subsolar point. If you know the noon sun angle and the subsolar point, you can find where you are. So the noon sun angle is 60 degrees. So instead of trying to solve for the noon sun angle, I'm telling you what the angle is. The noon sun angle is 60 degrees. We are at 45 degrees north, and the angle of the sun over the horizon is 60 degrees. Okay, so the noon sun angle equals 90 minus the zenith angle. So we know that the zenith angle equals 30 degrees, and 30 degrees is how far away from the subsolar point you are. So you're 30 degrees away from the subsolar point. Now, the people in this class who are really good at math would have realized there's 2 solutions to this. Because all I've said is you're 30 degrees away from the subsolar point. You could be 30 degrees north, or you could be 30 degrees south. So the difference between 45 north and 15 north is 30 degrees. So the subsolar point could be 15 degrees. The other solution would be 45 north at the subsolar point. If the subsolar point was at 75 north, that would also be 30 degrees away from the subsolar point. Give me my pointer back. So the difference between 45 north and 75 north is 30 degrees. So the difference between 45 north and 75 north is 30 degrees. So that's another solution, except that the subsolar point is never farther north than 23.5 degrees. So the only solution for this problem would be the subsolar point has to be at 15 degrees north. So I'm not going to give you problems like that. That would just be way too difficult, because there's an easier way of doing this. And that is, you tell people which horizon the sun is over. So if you know which horizon the sun is over, so for example, If you're north of, in fact, if you're north of the equator on this day, you're going to be looking south. So the South Pole's down here. If you were north of the equator on this day, you'd be looking at the sun, and the sun would be over the southern horizon. If you were south of the equator on this day, the sun would be over your northern horizon, because you'd be looking northward in order to see the sun. Since the subsolar point is on the equator, if you're south of the equator, you have to look north. If the subsolar point's the equator and you're north of the equator, the sun is south. So, which horizon is the sun over? If you were at A, the sun is over the southern horizon. You're looking south. If you're at B, the sun is over the northern horizon because you're looking north. In fact, if you're at A, it doesn't matter the season. The highest north the sun's going to go is the Tropic of Cancer. So if you're north of the Tropic of Cancer, the sun is always over the southern horizon. Same deal. If you are south of the Tropic of Capricorn, the sun is always over the northern horizon. What if you're in the tropics, though? Well, if you're north of the tropics, the sun is always over the southern horizon. If you're south of the tropics, the sun is always over the northern horizon. But if you're in the tropics, depending on your latitude and the time of year, like if you're on the equator, 2 days a year, the sun's going to be directly overhead. Half the year, the sun is going to be over the northern horizon, and half the year, the sun's going to be over the southern horizon. So if you're in the tropics, the sun for part of the year is going to be overhead, part of the year at the northern horizon, part of the year at the southern horizon. Okay, let's do a more advanced one. So in this one, I'm going to give you 2 elements and ask you to figure out the third, but instead of asking you to figure out what the noon-sun angle is, I'm giving you the noon-sun angle. I'm telling you the noon-sun angle is 73.5 degrees over the northern horizon. So automatically you know that you are south of wherever the subsolar point is. If you have to look north to see the sun, you're south of the sun. If you have a friend that's taller, you look up to see them. If you have a friend that's shorter than you are, you have to look down because you're above them. Same way, if you're looking north to see the sun, you're south of it. So the latitude of the subsolar point, I have to give you, it's 23.5 degrees north, and I'm asking you to solve for our latitude. We know that the noon-sun angle is 73.5 degrees angle, is 73.5. We know that we are 16.5 degrees away from the subsolar point. 90 minus the zenith angle equals 73.5. The difference between our latitude and the subsolar point minus 90 minus that difference is 73.5. So solving for that, we get 16.5. So that tells us we're 16.5 degrees away from the subsolar point. So there's 2 solutions, right? We could either be at 40 degrees north, because that's 16.5 degrees away from the subsolar point going one way, going north, and then going south, because it's an add or subtract. So that if the subsolar point is 23.5, you could either be 16.5 degrees farther north or 16.5 degrees farther south. So those 2 options for us to be are either 40 degrees north or 7 degrees north, because both of those are getting the sun at a 73.5 degree angle, because they're both 16.5 degrees away from where the subsolar point is. However, as I stated in the setup, the sun is over the northern horizon. So if we were at 40 degrees north, that's north of the subsolar point, so we'd be looking at the southern horizon. If we were at 7 degrees north, that's south of the subsolar point, so we'd be looking north. So the only answer that works is 7 degrees north, because we know the subsolar point is 23.5 degrees north. That's farther north. 23.5 is farther north than 7 north. So that's the only location that is valid for this question. Whew! That was fun. I will put up some practice problems in addition to the quiz, the pre-quiz, and the activity for this. Just some Google Sheets that you can go through and work on noon sun angles on your own to get you ready for the midterm. Good job, everybody. Good job hanging in. Maybe take a break, come back, finish this. The next topic is easier. There's no math, but whatever. Treat yourself. Daily insolation. So this graph is one of the ugliest graphs that you will see all semester. In fact, it is. This is the most complicated graph you will see all semester. This is a graph of watts per square meter per day received at the top of the atmosphere. So watts per square meter per day received at the top of the atmosphere. So across the top, there's time. January, February, March, April, May, June, July, December. And across the left side, there is latitude going from the North Pole, 40 degrees north, New York, Rome, Dixon. There's the equator, 40 degrees south, Antarctic Circle, South Pole. So watts per day. The numbers represent watts per day. From here to here is 0. From here to here is 50. 50 to 100, 100 to 150, 150 to 200, and so on, up to a max of, in the northern hemisphere, 450 watts. In the southern hemisphere, actually 500 is the most in the northern hemisphere. 500, so 400, 450, 5. The southern hemisphere, 550 watts is the highest value. At the intersection of time and space is energy in watts per square meter. What does that mean? Let's take a look. So we've got January, we've got the March equinox with a dotted line, we've got the June solstice with a dotted line, we've got the September equinox with a dotted line, we've got the December solstice, and I just treat the what is that, the left-hand side of each box. That's January 1st, that's the middle of the month, that's February 1st, March 1st, April 1st, May 1st. So if I'm asking you questions like, on August 1st, what's the value? Go with the left-hand line for the August column. September 1st, October 1st, November 1st, December 1st. So across the top, we've got time. Across the side, we've got latitude. Again, some latitudes 40 north, 23.5. There's a little tick mark for the tropics. There's a little tick mark for the Antarctic Circle and the Arctic Circle. So you find the date, June solstice, find the latitude, the equator, then you read the value from the closest curved line. So the intersection is right there of that time and the space, and you look for the curved line that's closest. In this case, it's smack dab on the 400 watts line. So if I asked you what is the daily insolation at the equator on the June solstice, the answer is 400 watts. 400 watts per square meter per day. So if I asked you on the June solstice at 50 degrees north, you go, well, that's 450, that's 500. I'm just going to call it 475. It's close enough. And it is. That's close enough. So if it's in between, if there's enough space, like that would be 350, that would be 400. So that's 375. Just estimate. And then this is the profile for any one of those latitudes. So at the North Pole, it goes from nothing. During the winter, the sun pops up about 500 watts a day for the summer solstice. And then September on the equinox, the sun goes below the horizon and stays there for 6 months. New York City going from under 200 to over 400. The equator, you can see there's virtually no difference between summer and winter and spring and fall. There's a little tiny dip in June, but that's about it. And then South Pole is the opposite of the North Pole, except the South Pole has 550 watts. Then you got 6 months of darkness, then back up to 550 watts. So a good question would be to discuss the shape of these curves as a function of latitude. So how does latitude affect the seasonal differences in insolation? So the equator, virtually no change. New York, 40 degrees away from the equator, a bigger difference over the course of the year. And then at the North Pole, an even bigger difference, going from 0 for 6 months up to 500 and then back down to 0. So this is just at 40 degrees north. So if you plotted out those values along 40 degrees north and the equator and the North Pole and the South Pole, yeah, you'd end up with that. And that's it. I think that takes care of how to read that chart, how to calculate the noon sun angle, or how to calculate your latitude, or how to calculate the location of the subsolar point, and how to read the analemma. I wish you good luck on Lab 3.